Howdy, today I'm Flippin Science looking at dipole-dipole interactions. So dipole-dipole bonding, dipole-dipole interactions, or dipole-dipole forces. This is attraction between polar molecules, and these are molecules that have a permanent pole. So the partial positive charge of one molecule attracts the partial negative charge of another molecule, and this happens over and over and over again. Since you have electrostatic attraction between a positive and a negative, there's attraction there that requires heat energy to break. So the end result is that if you have dipole-dipole bonding existing in your compound, you increase the boiling point of that compound. So here's a good example down here, hydrochloric acid. So the chlorine is more electronegative than the hydrogen, so in this covalent bond the electrons are spending more time around the chlorine. That gives it a partial negative charge, and the hydrogen gets a partial positive charge. The partial negative of this chlorine is attracting the partial positive of a nearby hydrogen. Now I've got this happening in a straight line, but it also happens vertically and all the way around. So what this means is that you get a lot of attraction between the molecules, and since there's a lot of attraction, that requires a lot more heat energy to separate. And by separate I mean breaking these bonds between the molecules, not within the molecules, between the molecules. And that's how you boil the compound. So let's look at another example. Let's look at iodine chloride. So for this we need to figure out which one's going to be more electronegative, and for that we need to think of our rules on the periodic table. So in our periodic table we can see that iodine is down here and chlorine is up here. So the rules of electronegativity are the higher you go up and the further you go to the right you are, the higher the electronegativity, if we ignore the noble gases. So that means chlorine is going to be more electronegative. So, and that's what we see in this picture. So the chlorine is more electronegative, so it's pulling the electrons in that bond towards the chlorine. That gives the chlorine a partial negative charge, so delta negative. The iodine gets a partial positive charge since the electrons are spending more time around the chlorine, so it has less negative because the electrons aren't there as much. So we get attraction between the delta negative chlorine of one molecule and the delta positive iodine of another molecule. That's what this dotted line is being represented by. So because of that, the boiling point of iodine chloride will be slightly higher than if we didn't have this difference in polarity between the atoms in the bond. So the strength of dipole-dipole attractions depends on a few things. So it depends on how far away the molecules are from each other, and that's determined by temperature, but also bond length, so how long the covalent bond is, but we're not going to go into that in much detail. But the key thing is the difference in charge between the poles. So the greater the electronegativity difference, the greater the difference in charge between the poles, and that means your delta negative will have a stronger delta negative, and your delta positive will have a stronger delta positive if the difference in electronegativity between the atoms is greater. So let's have a look at an example here. So here we have hydrofluoric acid, and here we have hydroiodic acid. Hydrogen iodide. If we have a look at this fluorine, again, if we go back to our periodic table, we can see that fluorine is further up and towards the right than iodine down here. So because of that, fluorine is more electronegative. So therefore, the delta negative charge here on the fluoride is going to be greater in size than the delta negative on the iodine over here in the hydrogen iodide. So because of that, the pole strength is stronger on either end of the molecule, and that means the attraction between one molecule and the next is also stronger. And therefore you require more heat energy to separate the molecules by breaking those secondary bonds, and therefore you get a higher boiling point. So if we look at the boiling points of these, we can see that hydrofluoric acid is a liquid, nearly a liquid at room temperature, whereas hydrogen iodide, its boiling point is -35, so it's going to be a gas at room temperature. So let's have a look at the trend for hydrogen halides. So we're going down the periodic table from hydrogen fluoride down to hydrogen iodide. We can see that hydrogen fluoride has got a really high boiling point, so it's close to being a liquid at room temperature. If we look at hydrogen chloride, we can see it's very low, and then hydrogen bromide is higher, and then hydrogen iodine is higher. Now, if it was just down to electronegativity, we would expect hydrogen chloride to be higher than hydrogen iodide. The reason for that is the chloride part here is more electronegative than the iodide part is. But that's not the trend we see. The reason why we're getting a different trend here is as we're going down the periodic table, the atoms are getting bigger. So because the atoms are getting bigger, there's more electrons, and that means the strength of the dispersion forces, so another type of secondary interaction, is getting stronger the further down we go. So as we go down, we're getting more electrons. So the chances of them pulling at one end of the molecule or the other, we have more electrons that will pull, so that gives a greater partial negative charge, so that has an impact on the boiling point as well. So it's not just, when we're looking at these things, it's not just one type of bonding happening. Dispersion forces are occurring between all of your molecules. But for these polar molecules, we can see there's a dipole-dipole aspect to their bonding between molecules as well, and that has an impact on the boiling point too. So far we've just been talking about diatomic, so hydrogen fluoride, there's 2 atoms in there. But this works in any polyatomic molecule that has a dipole as well. So here we've got hydrogen sulfide, H2S. This has a permanent dipole around the sulfur as well, so we will get dipole-dipole bonding between the sulfur, which is delta negative on one molecule, and the hydrogen, which is delta positive on another. And again, this will happen all between all the molecules in your compound. So this happens with polyatomic molecules too. There's a special case of dipole-dipole bonding called hydrogen bonding, which we're going to look at in a different video. This is stronger than regular dipole-dipole bonding, and the reason for that is the electronegativity of the atoms involved in the bond is greater. But we'll look at that in another video. Water is a great example of a compound that does hydrogen bonding. So, now for science, we looked at dipole-dipole interactions, dipole-dipole bonding, or dipole-dipole forces. That's it for Flippin Science today. See ya.